Okay, welcome everybody. It's 1 o'clock Tuesday, Central Time, 1 o'clock. That means it's time for our HDF clinic. Welcome everybody. For all of you who were able to join us here today. We'll just go through our usual motions. Before I start, I would like to ask, does anybody have any questions that you want to ask now or later? We'll stop many more times and give everybody an opportunity to ask a question about HDF, your applications. No? Okay, then we'll just move on. Your questions. Okay, there weren't any questions in our Google Sheet, so that's okay. I still have 2 questions left over from last time, and I haven't gotten answers or complete answers yet. So I'm going to leave them here, and I'm going to remove them once we get them answered. One was related to a note on the 110 release page about compatibility issues, and then this somewhat obscure comment about not all HDF 110 releases are compatible. So I want to figure out what that exactly means. And the other question then was, can you mix and match selections when reading and writing data? More specifically, let's say I have a point selection in memory and I would like to write to a hyperslab selection in the file, or the other way around. Is that supported, and does that work in parallel? I'm somewhat positive. I think that should definitely work. I don't see a reason why that wouldn't work. Whether it's supported in parallel is another question. What I can tell you is what is definitely not supported is that for these selections, we support certain set theoretical operations like unions and intersections and so forth. And the only limitation there is that these set theoretic operations are supported among hyperslabs. So you can take the union of the selections corresponding to 2 hyperslabs, and you can do that also with point selections, take the union or the intersection of 2 point selections. However, that, call it algebra, is not supported when one of the operands, so to speak, is a point selection, the other is a hyperslab selection. But that has nothing to do with this question here. So I'm getting your answers. Bear with me. Last week's highlights, I'm going to pause for a moment before I get into last week's highlights. Are there any questions about that or anything else? No? Okay, then I will just press on here. And last week's highlights. On the forum, we had an announcement just yesterday of the release, the beta release of Hermes. And Hermes is a distributed I/O buffering system for storage hierarchies. And there will be a webinar on December 1st, so stay tuned for that announcement. Sort of in high-level terms, you might say, well, is this something I should consider using, or what does that have to do with HDF5 and so forth? Well, I would say if you use a system where you have sort of a distinct storage hierarchy, and what I mean by that is, okay, you have RAM first and foremost. On a very modern system, you might even have PMEM, persistent memory. But then you might have locally attached SSD drives. You might have arrays of SSDs, for example, attached through a very fast interconnect. As another layer in that storage hierarchy, you might have a parallel file system mounted and so forth. So in a situation like that, you might consider trying Hermes, because what it in a way lets you do is, if you have an application, your application currently either uses only the parallel file system, and otherwise, if you want to use any of these other tiers, if you wish, of the storage hierarchy, you have to write code. You have to modify your application to take advantage of these faster storage layers, and you might have actually implemented some buffering of your own where you are consolidating or aggregating read requests and write requests just to get better performance from your parallel file system. And this is where Hermes actually comes in, where rather than you having to modify your code and actually explicitly targeting that hierarchy, just imagine going to another machine where the hierarchy is different or absent or something like that. Well, either you write your code to really discover that dynamically, or you have to change your hierarchy. So that would be a situation where Hermes can help you. What it basically does is it gives you a way to basically declaratively set aside resources, in this case, portions of RAM, portions of a locally attached SSD, portions of that, let's say, fast interconnect attached SSD array, and even portions of your parallel file system to use for buffering purposes. And then Hermes will basically implement, call it a buffer manager, a buffer pool manager, that as you are doing IO, read and write requests, let's say, it will manage those resources for you. And also in a more advanced stage, do prefetching for you, for example, on the read side, or asynchronous aggressive flushing on the write side. So yeah, but I invite you to go take a look at that announcement and then check out the GitHub repo. There is a getting started guide. And again, there will be a webinar on Hermes on December 1st. And also, we had that last time already, please, if this is a use case for you meaning you would like to do what people sometimes call online analysis, meaning you do some kind of data acquisition where you are writing to an HDF5 file, and that, let's call it experiment, runs for several hours or days, and so you would like to start the analysis or look at the data to make a determination whether that experiment is actually meaningful and going in the right direction. You would like to read from that file. Well, that would be a typical use case for Swimmer, single writer, multiple reader. And so, yeah, check out that forum post and then the GitHub repo. And that team is close to release and is really looking for feedback if they've missed anything in terms of robustness, perhaps performance, and so forth. So keep that in mind. I'm going to pause here. Any questions up to this point about HDF5, your applications, about the things that I mentioned? No? Okay, great. Then let's just press on. Let's look at the forum. Lots of things happening on the forum. There was one comment from Jordan Henderson, one of our developers, who is the main developer behind parallel compression. He said there was an issue on the forum that was outstanding for a while, where people reported issues, potential crashes due to truncation of the file. And Jordan believes that he came up with a fix, and that fix is probably already in develop, but it's definitely going to the branches, the development branches, sort of to the heads of the 113 release, which is developed at this point, 112 and 110. So once the next releases of 112 and 110 are rolling around, that fix will be in there. And yeah, if you've been affected by this, definitely give it a try, see if it fixes your issue. We know that using compression with MPI is a very popular feature, and so yeah, anything we can do to help that and solve issues, we definitely want to do that. Next one up There was an interesting comment by someone related to compound types. So the way I understand the description from this user is that I think the user says that he or she has to write, is using a compound data type, meaning think C-struct, think something that has distinct fields, named fields. And unfortunately for legacy purposes, they have to write these records, that's pretty much what a record is, one at a time. Now, the problem here is, of course, well, number one, that user is forced to do that for legacy reasons, so that's understandable. They have to do what they need to do. But of course, in general, of course, from an HDF perspective, that's typically not what you would do. So we understand that this is a legacy use case in a way, but yeah, typically you would write batches of records just to get decent performance. And but in this particular case where you are writing one record at a time, what happens is what I would call partial I/O gets in the way. What I mean by that is one of the interesting features for some use cases with compound types, as we call them, is that you can read or write just a subset of fields. So you can create a data set of that record type, and if for some reason, let's say that record type has fields A, B, and C, and your application is such that for some reason you get the A's, the B's, and the C fields in different at different times, so you can't really write them all at once. That's okay. With compound types, if you do an H5D write, for example, you can write just the A fields, just the B fields, or the A and B fields, but not the C field, and so forth. That's all supported. But that of course gets in the way here, because the HDF5, the way a request like that for both read and write is processed is of course that the library first has to do a matching on field names. And of course, the order of the fields in the file does not have to be the same as the order of the fields in memory, and then add to that subsetting so that you have 3 fields on that data type in the file, but you have only a struct that has 2 fields. And let's say instead of A and B as they are in the file, you have them as B and A. Then what the library, of course, has to do is it first has to determine, okay, in which order are the fields provided, and then potentially do sort of strided I/O rather than contiguous I/O. And this is what's referred to as, yeah, is it sorted by fields, meaning by field name, or by the offset of the field in that record type. And this has to happen, unfortunately, in each write call, because the library cannot assume that the buffer that you are providing in memory hasn't changed. And so this hurts. If you have a batch of records, that's fine, because the library, I think, can safely assume that for that batch, that order does not change. However, if you keep calling H5D write repeatedly, and in this case you have a batch of a single element, a batch of 1, then of course you start feeling this overhead introduced by this resorting. And then the question is, can this be avoided? And the answer is perhaps. But the user also said that if I were to provide a patch for this, would we accept it? And I believe Dana Robinson responded in yes, absolutely. We would, if somebody sees a clever way to avoid or definitely reduce that cost, that overhead to make that, albeit extreme use case of a single record at a time more performant, by all means, we we would definitely look into that. But that's sort of, it's an interesting, you might say it's an extreme, but yeah, it's legitimate. If you have an application, you have only so much flexibility to introduce HDF, so to speak, or just for proof of concept or prototype, that's what you have to do, and then you can improve from there. But yeah, we understand that sometimes that's difficult. Okay, I'm going to pause here for a moment. Are there any questions related to this, or no? Okay, I'll just press on. Here's another interesting one. Tomas, one of the key maintainers behind H5Pi, he said he created a pull request for a feature that might be interesting to some people, which is, I copied here the example from his pull request. Obviously, in H5Pi, the Python module for HDF5, you can already do hyperslabbing with very clever NumPy indexing and so forth. But he also, this is what his pull request is about, is to support, let's say you have a multi-dimensional data set, in this case a two-dimensional data set, and you just provide a list of point coordinates here. So in this read use case, it would be what we in HDF jargon would call a point selection that selects a point with coordinate 0, 0, a point with coordinate 1, 0, and a point with coordinate 2, 2. You can pass that list of points to that read call, and then in return, you would get a list or a NumPy array with 3 elements of the values of that data set at these 3 points. And then in reverse, you might want to do the same thing for write. So let's say I provide a list of targets, a list of target coordinates again. And he probably supports both, where you provide either a single value, which would mean broadcast that single value to all 3 coordinates, or if you provide an array of a matching, a list, I keep saying array, but in Python this is actually list. You provide a list of matching length of values, then yeah, the assignment would be, okay, we assign 1 to 0, 0, 2 to 1, 0, and the value 3 to 2, 2. And so I added a link here. This is his pull request, and he was looking for people for whom this might be a use case. He said he himself is not a sort of very highly demanded use case for him, but hey, that's, I mean, the beauty of it is that these dedicated developers, they care about more than just their own use cases. And so this is an invitation for the community to comment and get involved and maybe improve on something or test it for starters. And so yeah, I think it's a nice little feature. It makes working with point selections a lot more convenient, because as he points out, I believe in his post, is that currently it is supported through Boolean masks and so forth, but this, I think, gives people a lot more flexibility to work with point lists, which may come from a completely different module that doesn't have to do anything with Boolean arrays or masks or something like that. So this is very explicit and very convenient, I think. Okay. Next. So this is just sort of a comment. We talked about that last week, where a user was trying to read variable length data from an HDF5 file using a C++ API. And we talked about it, yeah, there was a little bit of a mismatch between the in-memory type and the in-file type. And he basically, he did the right thing on the right side, where, as we all know, for variable length types, you have to create these arrays of H5VL_T structs that are basically these pairs of a length and a pointer. And he was writing that to the file and everything was fine. But then he tried to read that back directly into a ragged array. So a ragged array is basically an array of pointers where the pointer then points to, let's say, a one-dimensional array of that element type. And yeah, that's something that's not supported currently with H5D read and H5D write, with the exception of strings. The only exception here are strings. So if you have variable length strings, an array of pointers essentially to character sequences, then in that case the HDF5 library will automatically do the conversion internally, or it will recognize, well, we don't really need these cumbersome H5VL_T things. I'm just taking from the user that array of pointers, and each pointer points to the bytes that make up that string, depending on what the encoding is, if it's ASCII or UTF-8 or something like that. And so the HDF5 library as a convenience supports that for both H5D read and H5D write. However, strings in this case are the exception. If you do that with variable length integer sequences, for example, or double sequences, or even more complex types, it doesn't work. You have to work with these H5VLT structures, and the whole thing is a lot more cumbersome. Now, the underlying fundamental problem is, of course, both on the right side, you may have the actual values that you want to write to these sequences contiguously in memory, and then you just have to create an auxiliary pointer array where you basically put these pointers, set these pointers so that they point to the location in that global contiguous array where that particular sequence begins, and then where the next begins, and so forth. But of course, on the read side, that doesn't work, because when you do an H5D read, you have to pass it an array of H5VL_T, and in this case, the HDF5 library will be the one initializing these pointer components. So and we'll talk about this in a moment, you actually are then responsible for reclaiming that memory, because the HDF5 library will be allocating space for the actual payload for the elements of that variable length sequence. But you own that memory the moment that H5D read call succeeds, and you are taking ownership of these. And then you would have to use a function like H5D VLAN reclaim up until the HDF5 110 series of releases. Or there was actually a new call introduced, a new API introduced in HDF5 112 called H5T reclaim, which essentially does the same thing. It's just maybe developers realized that, yeah, this is maybe something that really belongs with the sort of with the type module rather than the dataset module. And there are also ways, and this is for advanced users, you can actually overload so what H5D VLAN reclaim by default does is it basically iterates over that buffer and frees the memory that's attached to all these pointers. However, there are APIs where you can register a callback with the library if you're doing your own management, your own memory management and so forth. But then again, this is a feature for advanced users and requires more code and everything and introduces complexity. Now, since that user was talking about C++, of course, in C++20, we saw the introduction, I believe in C++17 or even in C++14, C++ introduced this notion of a string view. So where people already noticed, yeah, in string manipulations and so forth, frequently you lose a lot of performance by copying stuff around and so forth. And you lose performance because of the copying, but also the memory footprint increases and so forth. So they introduced string views. I don't remember if it was C++ 14 or 17. But then as of C++ 20, you can have these spans, which are in a way views on a contiguous array. So to express a ragged array, you could actually have just a vector of these spans, which would then point to contiguous regions in a sort of globally allocated contiguous array. But then on the flip side of that, how many codes are out there nowadays that are ready for C++ 20 or that support C++ 20 or for which C++ 20 is a requirement? I mean, maybe the number of C++ 11 codes is now picking up, but yeah, it's sort of the usual problem. What's the adoption rate? I'm going to pause here quickly and then quickly talk about tips and tricks. This is something we didn't get to last time, but it's sort of related to this question about matching reads and writes, as simple as it sounds. I just wanted to be clear about that. But before I do that, I want to pause and ask, are there any questions?
No questions, Gerd.
Okay, thank you. Okay, then let's jump into that. So to me, H5D read and H5D write are actually two of the oldest functions, I would say, in the HDF5 library that haven't really changed much at all, and that's a good thing. And there is, of course, since they correspond in a way to transfer functions in the sense that you are transferring stuff from memory into a file. That file might be in the file system, but it could also be a file that's also in memory. So, but it's a transfer function in one direction. And H5D read is also a transfer function just in the other direction. And there is an interesting symmetry between them. So when it comes to how do I read what I wrote, and sort of, if you wish, I would express this, what are the necessary conditions for that symmetry to work so that you can successfully read what you wrote? Okay, so again, just optically, it's clear that they have a very similar structure. The first is the dataset handle. The second is the in-memory, is an in-memory type handle. And then you might say, well, don't we need to know what's in the file? And the answer is no. The library actually knows what's in the file. So the library can figure out, since that data set exists in the file, in the logical file, the library can figure out, yeah, the metadata, the type class and whatnot, the specific structure of that in-file type. So that's why there is only one type argument with both read and write, because the file data type is known. However, then we are sort of describing selections in memory and in the file. And again, as any good transfer function, or any transfer function that is useful, there can be great variety. So for example, if you want to look at it as from a perspective of dimensionality, you can write from a 6-dimensional array to a 2-dimensional array, or the other way around. It doesn't really matter. As long as the counts in terms of number of elements of these match, there's absolutely no problem, and the library has no problem with handling that situation. And then the remaining two arguments are a dataset transfer property list. So that's typically interesting if you want to do transformations on the fly, or use something like MPI, collective versus independent, and so forth. And then the actual buffer itself, from which you are taking elements, writing them to the file, or into which you are reading elements from the file. Now, what are the necessary conditions for this to work out in a way to construct a read call that matches a write call? Well, number one, looking at the in-memory type, it is necessary that the in-memory type is convertible to or from, depending if it's read or write, to the in-file data type. So it's okay to write integers to floating point numbers, or even to read floating point numbers into integers. Of course, there will be truncation occurring, but that's fine. These are conversions that are actually, as we call, hard conversions that the compiler can generate, or there might be a user registered conversion function, but it's necessary that the in-file type and the in-memory type are convertible. And that brings us back to our earlier variable length discussion, where with the exception of variable length strings, if the element type of that buffer here is H5VLT, then this will be mapped perfectly well to variable length sequence types in the file. However, on read, if you pass a ragged array, a pointer to a ragged array here, unfortunately, these H5VL type structures are not convertible to an arbitrary ragged array type. And so an H5D read call in this case would fail. And the user corrected that, and then everything works. So if this is an array to H5VL_T, then this is going to be just fine. So symmetry on the type. Next one up, matching selections. Yeah. Basically the same number of selected elements. The rank or the dimensionality of the space is actually irrelevant. It is really about, do you have the same number of elements selected in memory and in the file? And one thing I would point out, there is this sort of this catch-all H5S all, and if you use it for both arguments, you are fine. You're basically saying, well, that the elements in this buffer pretty much cover the whole data space declared in the file, and you're just saying, just do it, and things go well. However, if you're using H5S all only for one of these arguments, then, oh, I misspelled that here, I gotta fix that. If you're using it only for one of them, you're basically saying, well, take the selection on the one that's not H5S all and apply it in memory. Let's say file space ID is something is not H5S all, but memspace ID is H5S all. You're basically saying, if this is not H5S all, but this is, will basically repeat or reflect this selection onto the memory space ID or the other way around. And sometimes people think, well, if this is H5S all and this is not H5S all, it somehow takes the entire memory space. And this is what H5S all unfortunately suggests, and then maps it on what's selected here. And then typically the number of elements selected in here is different from the number of elements selected in here. And that's when you get an error from H5D read or H5D write. So be careful when using H5S all, and we might come back to that another time. And then the buffers must have enough capacity to hold at least the number of selected elements. So on reading, if this array is bigger than what's actually being read, that's okay. Likewise, if this array is bigger than the actual number of elements that you are writing to the file, that's all good. HDF doesn't mind if that array is a little bigger. There is no bounds checking, if you wish, going on here. But of course, if this array is too small, you just get a segmentation fault because you are trying to overwrite memory that you haven't allocated, that you don't own. And of course, with the caveat that in the parallel case, it is okay that different ranks write or read different numbers of elements. And then of course, on the total side, so if you take the total number of elements selected in the file and the total number of elements selected by all ranks, those must match. And then for the buffer sizes, yeah, obviously it applies, this restriction applies per rank. And so it's not rocket science or something that I think most people will realize sooner or later, but I thought it might be worth just pointing that out. Okay, and I'm afraid we are out of time. We are over time. I thank everybody for coming, and yeah, see you next time.
Okay, thank you very much.
Thank you. Bye.